My name is Taniya, and today I'll be presenting my research that I've been working on for the past 6 months at the University of Glasgow. It's on the passive brain-computer interface for measuring cognitive engagement of virtual reality rehabilitation games. So just a little bit of background into the research. I was focusing on stroke rehabilitation. So what is it? Stroke rehabilitation involves repetitive task-oriented training to promote neuroplasticity and motor recovery, and this helps patients regain their lost functions as a result of stroke. However, there has been a challenge in maintaining patient engagement as prolonged therapy leads to frustration, fatigue, and boredom, and this has shown to reduce the efficiency of rehabilitation. Now, VR has emerged as a promising tool as it provides an immersive and rich environment to increase motivation and engagement, and this improves your rehabilitation efficiency. So what is engagement? Engagement is defined as a positive, fulfilling, work-related state of mind characterized by a strong desire to complete a specific task. So researchers have found specific brain activity associated with engagement, and they formulated the engagement index as shown over here. Brain activity can be characterized into different brain rhythms, and 3 of those rhythms, theta, alpha, and beta, have been used in this equation. Engagement is also affected by other mental states such as boredom and fatigue, and these are often considered indicators of disengagement. So how do we measure engagement? You can use subjective measures, which involve questionnaires like the NASA TLX, but this is not real time. You can't capture changes during therapy, and the results are highly variable between participants. An alternative would be to use an objective measure like an EEG-based BCI, which provides real-time monitoring of engagement based on physiological data, and it provides a method to introduce feedback into the participants or patients based on their performance. So for my research, I first wanted to identify the neurocorrelates of our brain activity of engagement, boredom, and fatigue from the literature, and I specifically looked into theta, alpha, and beta power. Then I wanted to design a passive EEG-based BCI to assess engagement and the other states, and for this I was collecting or recording EEG data while participants performed a task, which was playing a game. Finally, I wanted to compare my EEG results with the NASA TLX, which is my subjective measure, for validating the system. So after building or designing the passive BCI, I conducted experiments. I recruited 15 participants from the University of Glasgow, and during the experiments, they would play a simple game of Tetris while they wore the EEG headset, as you can see on the screens there. I recorded baseline or resting state recordings at the very start, which was your pre-resting state, and at the very end, which was your post-resting state. And this was simply them staring at a black cross against a white background screen for 2 minutes. Then I let them play a practice round, which helped them familiarize themselves with the game and its controls. And they also found a level that they were able to play comfortably at. This was followed by 5 gameplay trials, and each was played for 5 minutes at different game conditions. And after every trial, they filled out the NASA TLX form. So this was the EEG device that I used. It came with 8 electrodes, and it's shown in the positions over here. And this is how it looked on the participant's head during the experiment. Then for the game itself, there were 20 levels in total, and with each level increase, the block or the tetramino falls at a faster rate. There are 4 main game conditions, and the comfortable condition was played twice at the very start and end, and this was to induce different mental states. So comfortable was played at the normal level, which was self-selected by participants during the practice round. Restricted was played at an easy level, and I blocked one of the keys that prevented them from bringing the block down faster. This resulted in a much slower gameplay. The challenging and intense conditions were played at difficult and very difficult levels respectively, and all of them induced different mental states. Restricted induced boredom, comfortable induced fatigue, and the remaining induced engagement. So they also filled out 2 questionnaires. The first was a gaming experience questionnaire, and this was just at the very start of the experiment. to gauge their gaming experience and how well they knew Tetris. The next was the NASA TLX, and they filled it after every trial. So participants rated their experience against the 6 components on the questionnaire, and the average of the individual component scores were taken to calculate the overall workload score. So after doing some data processing and some analysis, I got the following results. First, looking at the neural correlates of engagement. From the literature, I expected to see an increase in the engagement index during the game conditions compared to the resting state. And this is what I saw in my results, as you can see in the graph here. Surprisingly, engagement index was highest in the restricted condition, which was to induce boredom. Then, so during the game conditions, it was much higher compared to the resting states. There was no statistical significance in my results, so it's hard to support the findings that I found here. Next, I looked into the neural correlates of boredom, and based on literature, I expected to see a decrease in theta and beta power and an increase in alpha power, all in the frontal region of the brain. And I was looking specifically at the restricted condition. So most of my results aligned with this. Theta did decrease over here at the restricted condition, which is the blue line here. And this decrease indicates decrease in game difficulty and decrease in or reduced cognitive load. Alpha did increase in the restricted condition, and this increase indicates wakeful relaxation and decrease in cognitive effort. Beta power surprisingly increased rather than the expected decrease, and increased beta is associated with increased attentional levels. And this suggested that participants were very focused on the game despite feeling bored. Also, they were very frustrated because of the slow gameplay, which could have aided in the increase. In terms of statistical significance, I only found it for the theta power, as you can see here, and none for the alpha and beta, so it's hard to fully support it. Next, I looked at the neurocorrelates of mental fatigue. And based on the literature, I expected to see an increase in theta power in the frontal region of the brain and an increase in alpha power at the parieto-occipital region, which is basically the back of the head. And I compared it between the post-resting and the pre-resting condition. So my results did align with this. In the case of theta power, there wasn't much of a difference between the post and pre-resting conditions. But when I looked at the last gameplay trial, which was comfortable too, I saw that it increased compared to the pre-resting condition. For alpha power, you can see that it did increase definitely in the post-resting compared to the pre-resting. And this increase suggests a decrease in alertness and disengagement from active cognitive processing. And there was also not enough statistical significance in these results. Finally, I looked at the NASA TLX scores, which was my subjective measure. So I calculated the overall workload score, and you can see from the graph that as the game difficulty increased, the workload score also increased. It was the highest in the intense condition and lowest in the restricted, which was inducing boredom. Also, you can see that there's a lot of variability between participant scores, which is how these dots are distributed. And this is likely because the participants interpreted the questions and the questionnaire differently. So in conclusion, I was successfully able to build a passive BCI based on an 8-electrode EEG system to monitor engagement in different states. The neural correlates of the mental states that I found in my results mostly aligned with those in literature, but there was not enough statistical significance to conclusively support the findings. Finally, I was unable to validate the EEG results with the NASA TLX results because there was no correlation with these two. The NASA TLX wasn't the best measure, but wasn't able to properly measure fatigue or engagement in my experimental setup. It did measure boredom to some extent because we saw the low scores earlier, but again, it just didn't measure engagement and fatigue as well. So for the future implications of my project, the findings from this research will be used to inform the design of an EEG-based BCI VR system for stroke rehabilitation. And this will involve bringing a game level change based on the participants' or patient's mental state as they play the game or do the rehabilitation task. And this is currently being worked on by a PhD student that I worked with during my research. So that's the end of my presentation. Thank you for listening, and I'm open to any questions.